Hello students, today we will discuss some more problems. Here is one theorem. The set of all solutions of the system Ax equal to 0 bar of m homogeneous linear equation, that is number of rows with n unknowns, is also a subspace of R power n. So we are taking one homogeneous equation here, Ax equal to 0 bar. Then suppose from this we are getting some finite number of linear equations. So how many number of rows are there? So that much number of homogeneous equations will form, and at the same time with n unknowns, how many number of columns are given, that much of unknowns are there, then it is obviously a subspace of R power n, whatever it is. Suppose here is one problem, H be a set of all vectors in R power 4. So R4 is a vector space here with coordinates a, b, c, d. They are nothing but unknowns here. Now it satisfies two equations are given here. Two equations are given. Then show that H is a subspace of R power 4. So already we have for any vector space, when you are taking in Ax equal to 0 bar form, first of all, for that first take this two equations and coefficient into that one, that is 1 into a minus 2 into b, like that we are writing here first, then converting into Ax equal to 0 bar form. So here from equation 1 we are converting like this, 1 into a minus 2 into b, like that. In the second equation we have minus a minus b, that is minus 1 into a minus 1 into b plus c. D is not given, that's why 0 into d equal to 0. So from these two equations we are taking as matrix separately and unknowns take separately, like first column as 1 minus 1, second column is minus 2 minus 1, third column, fourth column, into what are the unknowns here, a, b, c, d, take it in as x equal to 0 bar. 0 bar means here two zeros are given, so 0 bar. So it is like which form, Ax equal to 0 bar. So here what are the number of rows here, 2 rows and 1, 2, 3, 4 columns. So this is of 2 cross 4 matrix. So number of rows are 2 and number of columns are 4, and from this previous equation, previous theorem, homogeneous equations are equal to number of rows. So it is equal to 2, equations are 2 and number of rows are 2. In the same way, number of columns are 4 and unknowns are 4. So from this above theorem, what we can conclude, H is a subspace of R power 4. In the next problem, find the spanning set for the null space of one matrix. One matrix is given. Find the null space spanning set means null space is spanned by how many vectors, that all vectors of null space we need to find out for that. So for that, one matrix is given. To find the null space of A, first write the definition of null A. Here 1, 2, 3 and 1, 2, 3, 4, 5. 3 cross 5 matrix is given here. By definition of null A, obviously we know that null A is nothing but x is any vector which is from R power n such that Ax equal to 0 bar. Suppose it satisfies this equation, then this x is belongs to null A. So x belongs to R power n means number of columns are 5 here. So R power 5. So x belongs to R power 5 means we should take 5 unknowns for x, and 0 bar. 0 bar is from right side. So how many homogeneous equations are there, that much of zeros will come in 0 bar. That's why here 3 rows are there. So that's why we are taking here zeros. Then write it into Ax equal to 0 bar. Ax equal to 0 bar. Then actually we got 1, 2, 3 homogeneous equations. Then by solving that also we are getting, but like these problems we are also finding the vectors by using augmented matrix A 0 bar. So first do the row operation by taking augmented matrix, take A here and 0 bar is 0 0, and what are the possibilities are there, how much times we are taking operations, then it will become into 0, like that we are taking row operations to make maximum number of elements as 0. So here 1 is there, better to take in R1, then it will be easy to take the row operation. That's why we are changing R1 and R2 here, R1 and R2, interchanging R2 as R1, R1 as R2 here, and R3 as it is. Now here 1 is there. Here to make this into 0, what we should do, R2 implies R2 plus, when you are taking 3 into R1, then it will become 0, right? That's why R2 plus 3 into R1, then it will be 0. Again R2 means 6 here, 6 here plus 3 into R1 means minus 2. That is what, 6 minus 6 is 0. Again R2 plus 3 R1 plus 3, R1 means 2. 6 minus 1, 5. Like that we can take for everyone. Similarly, here R3 means R3 minus 2 into R1, then it will become into 0. So R3 minus 2 R1. Again, do as it is. R3 minus 2 R1 is 0. R3 minus of minus plus into plus 2 4 means 0 here. Like this. R3 means 5 minus 2 into this 4, that is 1. Like this we can do for everyone. Now here this divided by 5, then it is 1, it is 2, it is minus 2. Okay, now here same row, so take R3 implies R3 minus R2, then it will become 0. R2 minus R3 minus R2, R3 minus R2, R3 minus R2, then all values are 0. Now stop up to here, because when you are making this into 0, then this will become non-zero. So these are the maximum possibilities. So take this as it is and converting into again homogeneous equation. Actually, by taking the three normal first equations also we can do, but this is the simplest way to find the null vectors. So when you are taking into equations, what will happen? 1 into x1 minus 2 into x2 minus 2x2, 2 into x3 plus 3 into x4 minus 1 into x5 equal to 0 is one equation equal to 0. Again x0 into x1, 0 into x2, 1 into x3, 2 into x4 minus 2 into x5 equal to 0. So we have two equations. Now you can converting into dependent to in terms of independent variables. So take x3 equal to minus of this plus of this. Then x3 is depends on x4 and x5. So x4, x5 are independent variables. Similarly, take this equation x1 which is minus x2 and take this x3 as substitute this in this. Then we are getting x2, x4, x5 terms. Take x1 equal to take all the terms into this side. Then it will become x2, x4, x5. Now take the x vector x1, x2, x3, x4, x5. Now what is x1 here? Write this one. Again x2 is independent variable, so take it as it is. x3 depends on these two, so write down these two. x4, x5 are independent variables, so take it as it is. Now take x2 common from this. x2 is common in the sense first term is element is 2. In this x2 means 1. In this there is no x2, so 0. In this there is no x2, so 0. So here in simplest way, how you can write in the sense, you also write in this way, 2 into x2 plus 1 into x4 minus 3x5. Here x2 1 into x2. Here x4 term is not there, so 0 x4 plus 0 x5. Here x2 term is not there, 0 x2 minus 2 x4 plus 2 x5. Here x2 is not there, plus 1 x4 plus x5 is not there. Here x2 is not there, x4 is also not here, and 1 into x5. Then it will become easy to you. Now take x2 common means 0, 1, 0, 2, 1, 0, 0, 0. Plus x4 common means 1, 0, minus 2, 1, 0. Like this, x5 as common. Now it is like which form? x2 into v1, x4 into v2, x5 into v3. So this is a linear combination of these three vectors, right? Which satisfies the condition Ax equal to 0 bar. So obviously this x belongs to null A. So where this vector v1 equal to this, v2 equal to this, v3 equal to this, it is nothing but spanning set for null A is nothing but what? v1, v2, v3. So null A equal to v1, v2, v3. That's it. So one matrix is given. To find all null vectors means take augmented matrix A 0 bar, then do row operations, then converting into homogeneous equations. After that, take dependent variable in terms of independent variable and take independent variables as common. Then we are getting null space vectors. Now let us discuss another important topic, that is column space of a matrix. So null A means x must be belongs to R power n and Ax equal to 0 bar, then that x belongs to null A in this. But in column A, we are taking Ax equal to B. Ax equal to B, where B is belongs to column A. That is, column A is spanned by the vectors in columns of A. Suppose we are taking one matrix A whose first column is A1, second column is A2, like that we are taking n columns suppose. Then column A is spanned by each vector of columns of this A. Suppose, so each columns of A means how many columns here, how many number of rows, that much of columns are here. That's why it is a subspace of R power m. So A can be, suppose B is a vector in column A, can be written as Ax for some x, where the notation Ax stands for a linear combinations of vectors of A. So how you can define in column A? B we are taking, where B can be expressed as linear combinations of vectors of A, that is Ax, where x belongs to R power n. So, linear combination in the sense B can be written as what are the vectors of A, A1, A2 and so on up to An. So, we are taking as x1, A1 or A1, x1 plus A2, x2 and so on up to An, xn. That means, for example, suppose you are taking A as some 1, 2, 3, 4. This is called A. A1 is nothing but what? This total vector is considered as A1. This total vector is considered as A2 like this. So, in this, how many number of elements are there? 1, 2 like this means how many number of rows in A? That much of numbers in column A. That's why we are taking that it is a subspace of R power m. So, how you can define? Simply B equal to Ax like this we can define. Otherwise you can express as B equal to A1 x1 plus A2 x2 and so on up to An xn, where A1 A2 up to An are columns of A. Now it is a subspace of R power m obviously, and now show that a column space of m cross n is a subspace of R power m. So similarly, same as null space, it is a subspace of R power n, but whereas column A is a subspace of R power m. For that, see here, to prove column A is a subspace of R power m, Rm is a vector space and A is of m cross n matrix whose columns are A1, A2 and so on up to An. So when you are taking A1, then this contains number of rows, right? Number of rows are m, so the elements in A1 are m. So column A is equal to what? By definition B such that B equal to Ax, or you can write B can be expressed as linear combinations of vectors of all these matrix vectors, like B equal to A1 x1 or x1 A1 plus x2 A2 and so on up to xn An. So, to prove it is a subspace of R power m, obviously it is a non-empty subset of R power m, because in column A, every element must contain how many number of rows, that much of entries must be in column A. That's why it is a non-empty subset of R power m, and so it is enough to prove 0 bar belongs to column A. So, 0 bar belongs to column A means 0 bar can be written as, we can write it as, suppose A is what here, A1, A2 and so on up to An vectors, right? N number of vectors. So, we can write 0 bar as 0 into A1, 0 into A2 plus and so on up to 0 into An. So, it is nothing but linear combination of which vectors? A1, A2 to An. Linear combinations of vectors in A in the sense it is belongs to column A. That's why 0 bar belongs to column A. And also vector addition condition, U plus V belongs to column A. To prove this one, U belongs to column A in the sense U can be expressed as linear combinations of vectors in A, that is x1 A1 and so on up to xn An, where x1 to xn are scalars. In the same way, V belongs to column A means V also can be expressed as linear combination of these vectors. So, take some another scalars y1, y2, then we can write a linear combinations in terms of An, where y1 to yn are scalars. Now U plus V means when you are adding these two, A1 common, A2 common, then and so on up to An common here. Now this is also a linear combination of which vectors? Obviously A1, A2 and so on up to An, where these coefficients are scalars. So from this is a linear combinations of which vectors? Columns of A, that's why it is belongs to column A. So vector addition satisfied. Similarly, scalar multiplication means Cu. Cu means C into U. Then take Cx1 into A1 like that. So it is also a linear combinations of which vectors? A1, A2 and so on up to A1, which is from column A. That's why where belongs to, it is belongs to column A. So scalar multiplication also satisfied. From the above three conditions, what we can conclude? These are column A is a subspace of R power m. See some simple examples that find the vector which is belongs to column A.